Okay, let's get started, everyone. Hello, I'm Patrick Donnelly, work at Red Hat. I'm the CephFS tech lead. This is Jeff Layton. He's did a lot of the work on this project. He's got a, you want to give your background?
Been at Red Hat for quite some time and work on storage of all sorts. So.
Okay. All right, I should tell this time. So we're going to talk about deploying NFS clusters using Rook to export CephFS. To give a little introductory information on CephFS, for those who aren't already familiar with it, CephFS is one of the first use cases for Ceph, actually, at Lawrence Livermore, when they were first giving the grant to Sage. What they really wanted a file system, and what they ended up getting was an object store. So CephFS was what the first thing they were going to build on top of the object store. It provides a POSIX distributed file system. Some of the more notable features of it is that the MDSs form a cluster, and you have all the metadata stored separately, and that the clients have direct access to all the file data to do reads and writes. They don't have to talk to the MDSs to do those operations. So the clients and the MDS it's also notable that they cooperatively maintain a distributed cache of the metadata, including the inodes and the directories. The MDS hands out capabilities, which are similar to leases in other systems, that give the clients permission to actually do writes or reads on a given file, and that's how you don't have any kind of inconsistencies, especially with caches, where one client will be trying to write to a file and maybe buffer those writes while another client's trying to read them, and they disagree on the state of the file. And because of the way the system is set up that way, you have a certain degree of trust with the clients and how they behave. You are trusting them to obey what capabilities you've handed out to them, and they're not going to write to a file when they're not supposed to. We built 2 clients up to now, not up to now, but the 2 primary clients that are in use today are the CephFuse and the kernel client. The CephFuse client is typically our test bed for new features. It's also used sometimes for things like quotas prior to Mimic. The kernel client is where you're going to get all your performance. Yeah. So why on earth do we want to put an NFS gateway in front of CephFS? So some of the issues with having these trusted clients and well-behaving clients that we assume are going to behave well is that not all these clients may be able to speak Ceph properly, especially with the latest versions of Ceph. They might have a really old kernel that may be known to have bugs. It's not going to behave properly. Or the client's running on an operating system that is running a CephFuse that we don't know anything about. That may have some modifications. Another aspect is security. There might be a firewall protecting the Ceph cluster from, say, whatever compute is being done. Maybe the Ceph cluster is operating as a storage appliance for some research university, and you don't want the students to have access to whatever data might be on there, such as like biometrics and things that need to be protected by HIPAA regulations and rules. Another security aspect is you might want to protect the data via some authentication mechanism that Ceph doesn't yet support, for example, like Kerberos, although is slated to change in the future with Octopus. And then finally, one of the use cases we really had in mind when we began this work was OpenStack Manila, where we have tenant VMs that are wanting to cooperatively use a particular volume and part of the shared file system, and you don't want other tenant VMs to be able to talk to that, to manipulate that shared volume. And you also don't want those tenant VMs to have raw access to the storage network. You want them to go through some gatekeeper service like an NFS daemon to prevent them from manipulating data that they're not supposed to, or operating an old client that we know has bugs. So with that, I'm going to hand this off to Jeff.
So we've had active-passive gateways on top of CephFS for a long time. And essentially what that means is that we have, and these are pretty common and have been for a couple of decades now, but you can build a cluster for NFS that is where you have one main server and one sort of standby host, and then the main server fails, fails over to the other node. Those tend to scale pretty poorly. One of the problems is that at some point you're going to hit all you can do with a single server, and at that point, then you sort of hit a wall in performance. So we've had this for quite some time now, at least, and we've had a way to do this since Ceph Luminous as well, in an active-passive configuration. Typically you rely on some sort of third-party clustering software like Pacemaker or CoreSync, and people have built active-passive NFS clusters with stuff like Veritas clustering and that sort of thing too. But what we really want to get to is an active-active deployment. So when you see here, we've got in this other slide, we had all the clients, our various clients here are connected to one single node, and this other node's just kind of sitting there not doing anything. And so but really what we want to do is be able to scale out linearly, so that we can have multiple clients connected to different nodes and still have consistency guarantees and stateful, and allow them to manage state properly across the whole cluster. So when we embarked on this project, we had a number of goals. I don't know if anybody could, this text might be a little too small, but in any case, essentially we wanted to be able to scale out the cluster, linearly. So, if we decide we need, a bit more capacity, we can just add a new cluster node and keep running. Another goal we had was we wanted it to be containerizable. It's a new world now with containers and Kubernetes and that sort of thing, and we wanted to be able to leverage that infrastructure to make it easy to deploy these things. It's nice to be able to go into Kubernetes and just say, give me another cluster node. We also wanted, in order to do that, we decided to focus on NFS v4 1+. I'll talk about the NFS protocol here in a minute, but the 4.1 gives us a number of features and capabilities that earlier NFS versions didn't have. And then also we wanted to sort of minimize the need for third-party software like Pacemaker. If you have, we already have a cluster. We have a couple clusters, right? We have Kubernetes, and we also had Ceph. We didn't really want to add a third one in order to handle this. We figured that should be enough. So our daemon of choice for using NFS is NFS-Ganesha. So it's an open source NFS server, runs all in user land. And so that's kind of nice. It makes the containerizable portion quite easy. It has a plug-in backend, so we can plug in for different file systems. And one of the ones we can plug in that we're concerned with here is Ceph. It uses libCephFS, which is, Patrick talked about the Fuse client. It really is built on top of a library called libCephFS. And so Ganesha plugs into the same library and uses the same functionality to do its thing. And we also have the ability in Ganesha to store some of the out-of-band information in Rados directly. In particular, for NFS v4, and I'll talk about this again here in a bit, we need to be able to keep track of what clients have state at any given time. And we also need to track some configuration information in Rados as well. So all this kind of boils down that it's all pretty amenable to containerization. We run all this in user land. We don't need any, we're storing all the configuration, recovery info in Rados, so that there's really no permanent information we need to store on the local disk or anything. We don't need any really writable local file system storage. It runs completely unprivileged. We don't need any root privileges or anything like that in the container. And if the thing falls over and dies, we can just spin up a whole brand new container from the read-only image and not have to try to do that sort of failover dance that's pretty common with traditional clustering. So I'll step back here for a second and I'll talk about the NFS protocol. So the NFS protocol is pretty old. I mean, it started in the 80s by Sun. Early versions were all stateless, so they didn't have any state at all. We didn't keep track of what files were open or whether locks were held or anything like that. And those were all done by bolt-on protocols that were added to the side. And then in the early 2000s, we had NFS v4 was presented. And for that, we needed it to be stateful, and that was mainly done so we could handle locking in the core protocol. And then about a decade after that, we have a new protocol that came out, NFS v4.1. For that, it added a number of features. One thing was a sessions layer, which made it easier to do exactly one semantics, which is necessary for NFS. And then we also, it added something that we rather like for this, which is it added a reclaim complete operation. See, prior NFS protocols didn't tell the server when they were finished reclaiming objects, so it never knew if another reclaim operation would come in at any given time. And so you always had to wait for the full grace period. We'll talk about that again in a minute. The reclaim complete operation makes it so that we can keep track of which clients are connected back and and completed their reclaim. And if that happens, we can lift the grace period early. And it also has some features for clustering and migration, so that we wanted to be able to use in this configuration. And then we also have an NFS v4.2 that's come out fairly recently, and it's mostly just smaller features on top of v4.1, but it's pretty similar to protocol. So the big challenge with any NFS server is that you have to deal with recovery. So most NFS servers don't track ephemeral state on stable storage. So what happens is, if the machine crashes and comes back, the clients have to reconnect to the server and tell it, I had this file open, I had this lock, I had this delegation, and so a lot of commercial NFS servers will do this by tracking detailed state on stable storage. So but that tends to be pretty expensive, performance-wise. And so Ganesha has. So what we do instead was we keep track of what clients had state which is necessary for certain corner cases that can occur if a machine reboots and comes back after a network partition. Ganesha has had support for storing this in Rados in single server configurations for a long time. It had some bugs, but we've cleaned those up pretty well now. So anyway, when a machine comes back, we establish what's called a grace period at the beginning. And then when the NFS server comes back, I should say. And during that time, no new state can be established. So if someone tries to do an open, they'll get an error back that says, try again a little later. And so we only allow reclaim requests during the grace period. So we're allowing clients to come back in and grab stuff that they had before. And then we only allow reclaim for clients that were present and held state at the time of the crash. So in order to track that, we have to keep track of what clients were holding that state on stable storage, so when the thing comes back, it knows. So prior to a client doing its first open, we set a stable storage record for it, and if there isn't one already, and then we remove it after the last file is closed, or when the client state expires, or when the client's lease expires. And then when we go to lift the grace period and move into normal operation, we have to atomically replace that database, replace the old client database with the new one. So another way to think about this is that we have actually multiple epochs. So you can think of a life of an NFS server as a series of reboot epochs. We start out, it comes up, it's in grace period. We transition into normal operation, and then when it crashes again, it comes back up, it's got a new epoch. At the start of each new epoch, as the clients perform their first open, we set a record for them in the database, and then during the grace period, allow clients that are present in the previous database to do the reclaim. And then whenever we are ready to move into the new grace, or out of the grace period, we do that atomic replacement so that the next time we reboot, we know exactly who was present at the time that the crash happened. And the key point here is the reason why this matters is that we can apply this epoch concept across a cluster of servers. So this is new in Ganesha. We wrote a new Rados recovery backend for Ganesha that keeps track of a coordinating database within Rados in a Rados object that's to allow multiple servers to coordinate what epoch is present, or what epoch we're in at the time, and which epochs we're allowed to recover from. So we do that with a couple of 64-bit integers. One, we have the current epoch, the one we're in now. And then we also have one for a recovery epoch. And then as we move from the grace period and into the normal operation phase, we zero out the recovery epoch to indicate that we're not allowing any more reclaim. But we also need a way for the servers who are loosely coupled to be able to indicate what their needs and their current state is. So we have a set of 2 flags per server that we also track. One is the need grace flag. So when the server comes back up, he says, "Whoop, I'm just crashed and came back. I need a grace period." So the other servers can then look at that, and then as they move into the grace, they can then go start enforcing a grace period that they probably won't allow any reclaim. And then they can say, when they are then enforcing the grace period, they can go and set a flag saying, "Hey, I'm enforcing now." And then at that point, the server that is crashed and come back can look and see and say, "Okay, is everybody in the cluster now enforcing the grace period? Great, I can go allow reclaim to happen." So the idea here was to move away from sort of a traditional way of doing this sort of thing, where we have you often have a central controlling entity that says, "Okay, everybody go into grace period now. Everybody come out of grace period now." That's a single point of failure. So I wanted to get away from that and do this in a way so that we have apply some really simple logic and information so that each node can sort of make its own decision about what it should do at that time. So that's interesting from the recovery aspect of it, but we also have some other issues here too. I mean, when we look at this sort of configuration, we're really layering NFS over any clustered file system. We are dealing with layering a network file system on top of a network file system effectively. And so when we do that, we have there are sessions. Each network file system has its own session sort of layer. And in the case of CephFS, both of those session and NFS, they're both lease-based mechanisms. So the protocols are stateful. We have leases that we have to deal with, or the clients have to maintain regular contact with the servers to make sure that they haven't dropped off the net. So we have some real challenges with this in that we have to deal with what may be interlocking timeouts with some of these sessions. So in effect, here's an example like on here is that, we may have a Ganesha server that crashes and then we start up a new one, right? Well, so the client issues a request to do an NFS reclaim. That new server then comes back and says, okay, I'm going to do an open through libCephFS, but now he's stuck because the CephFS client, the previous CephFS client that is now dead, is holding the caps that we need, that the news client needs in order to do the open. And so, the MDS session timeout defaults to 60 seconds, and usually our NFS grace periods are 90 to 120 seconds. So by the time that other client expires, we've already eaten into half the grace period. And it can be worse, right? If we have, it may be, there are other timeouts to deal with. We have lease timeouts and stuff, so the clients may not even come back immediately when the server reboots. So by the time we get around to everything being cleared out, it could be, the grace period could be all the way gone. And the session could also die, if it takes a long time for the server to reboot and come back, the MDS session could die before the server's returned at all. And at that point, another CephFS client could have raced in, grabbed a lock, a file lock, done some changes, and dropped that lock, and then the server coming back would be none the wiser. And that's bad, because then we're looking at silent data corruption. So we added another feature to Nautilus. An interface to allow Ceph clients to reclaim client sessions. So for now, it's so when a CephFS client drops abruptly, he just drops off the net. Let's say crashes. The MDS will keep the session around for a little while in case, because he doesn't know. I mean, it could just have been the network hiccup or something. So he's got to wait a while for the CephFS client to come back. But all the stateful info for this session or all the stateful info that the client holds is tied to those sessions. So we added new interfaces to libCephFS to allow the Ganesha to request that its old session be killed off immediately. So that gets us past this point where we don't have to wait around for that MDS session timeout in order to be able to get caps that we need to reclaim info. It also allows us to do things like extend that timeout so that we have a little extra time in case we have a real major problem that might prevent the server from rebooting and coming back pretty quickly. So eventually we want to be able to extend this interface too. That's sort of the long-term plan, is to extend this interface so that we can allow the client so we would allow the MDS to sort of hold those caps in escrow for this, for the new client coming back. So he would be able to reclaim against those old caps. So here's my token animation here. So here we have a single server, NFS server, Ganesha server that's connected to the Ceph cluster. He dies. News client comes back, or we spin up a new client or a new NFS server with the same node ID, and then he talks to the Ceph cluster that says, okay, go ahead and kill off that session now. Boom, it's gone. So that allows him to sort of take off and get back to running quickly. Eventually, like I said, we want to be able to allow it to do things, or to be able to reclaim stateful info that was held by the previous client, as that would allow us to avoid putting the whole cluster into grace. The other nodes could then just keep chugging along because we would know there'd be no conflict. I think I was going to turn back over to you at this point, so I'll turn back over to Patrick.
Yep. So the next challenge we wanted to address was scalability. This was one of our long-term goals. So in a lot of the NFS-Ganesha setups that are in the wild, it's currently an active-passive configuration. And what we wanted to allow was having multiple NFS-Ganesha servers in an active-active configuration that allows us to scale out horizontally for what the file system being exported. So you could have clients talk to multiple NFS servers. Another goal we would like to do is be able to scale in another direction too, by having an NFS cluster for each volume that is being exported within CephFS. And a volume, or nowadays we call it subvolumes, which would just be a directory tree that we want to export with Ganesha. Another way we could achieve scalability is by having an NFS cluster for each of those directory subvolumes, so that if assuming these these data sets are independent, you can just have clients relegated to a particular part of the subtree and only talking to a particular set of Ganeshas. Another challenge we needed to address with deploying these NFS gateways was handling failures through in dealing with IP migration, so that when one NFS-Ganesha server fails and another needs to take over for it, you need to move the IP address because NFS clients don't know how to have their IP address switched. With CephFS, this has not been an issue with the MDSs. As you may know, the MDSs also have standbys. And so when the active MDS fails for whatever reason and the monitors promote a standby to an active, the monitors distribute a new MDS map, which goes to all the MDSs and also all the CephFS clients. And they know what the new IP address of the new MDS is. There's no such service built into NFS, so the NFS clients have no idea that something is taken over. So you need some sort of infrastructure service to actually move the IP address over to another Ganesha daemon. So this is where Rook and Kubernetes come in. Rook was and Kubernetes are kind of a direction that Ceph was already heading in, and luckily Kubernetes also deals with the issue of IP migration for us during failover, and so it made it an attractive platform to target for this work. So as you may have seen in other talks, Rook is a cloud-native storage orchestrator. It's an operator that runs within Kubernetes and manages your Ceph cluster, sets up the cluster, manages it through its lifetime. For our work, we're also taking advantage of this new paradigm within Ceph, where the Ceph cluster itself is also aware of the orchestrator running under it. In this case, it would be Rook. And it can actually issue commands to the orchestrator to change how the Ceph cluster is deployed. For example, set up new OSDs. For this work, what we're wanting to do is we want the Ceph cluster to actually manage the NFS daemon. So the NFS gateways are now a first-class citizen within Ceph. And so we're going to take advantage of the orchestrator to have Ceph tell Rook to please deploy me a new NFS-Ganesha gateway container. So Rook is is handling all the details of actually deploying the container. So now Ceph doesn't have to worry about, all right, so I want to deploy Ganeshas on these 3 servers, and eventually I'll get around to using them. We don't have to deal with that nonsense. Rook will actually take care of the details of deploying those on demand. Again, we're taking advantage of the orchestrator, so this is going to let us scale up and down the NFS Ganesha servers. And also in the dashboard is going to allow us to set up the exports for the Ganesha daemons. This was somewhat a queer way of setting this up, but when the manager actually wants to configure the exports for the Ganesha servers, it's going to issue commands against the dashboard API which will actually go out to Rados and set up the configuration files for the Ganesha cluster. So what's interesting about this is that it's going to allow us to set up Ganesha servers on demand for a given subvolume that we want to export. And it's also going to allow us to scale that horizontally with the number of actives according to how popular that subvolume is. Initially, we'll just let the operator of the cluster set statically how many Ganeshas they want to set up. And this is kind of a direction we want to go in as the Ceph project as a whole, where again, Ceph is sort of managing itself and how it's being deployed and being able to dynamically modify itself. This sort of software-defined storage. Right now, we're looking at how we can do this with Ganesha and exporting, but we also want to look at this in CephFS in other aspects. For example, with deploying MDSs, being able to have CephFS, do some kind of introspection and detect that it needs to, it could benefit from having more MDSs and dynamically go out and add those. And then at some point in the future, when probably with an Octopus, when we have multi-file system support, and so you can actually create volumes, which would be multiple file systems. The Ceph cluster itself, the manager is going to be deciding that I need to deploy more MDSs in response to creating new file systems. And so as far as a vision for the future, we're not quite there yet with Nautilus. A lot of the building blocks are in place. We just have a few things to clean up and then backport into Nautilus, so you can kind of expect it within a few minor releases. Eventually where we want to get is we can create a subvolume, which is, again, just a little directory tree within CephFS. In this case, the file system is called vol.a, and the subdirectory that we're creating is called subvol1. This is a new volume manager plugin that we're building within CephFS, and it's going to allow you to have a single source of truth and essentially managed API for actually managing the volumes within CephFS. And then eventually, after you've set up this subvolume, we want to be able to just as simply as that say, turn on NFS sharing, and the Ceph manager goes out, configures the Ganesha exports for you, securely sets up the authentication credentials for that Ganesha server, and turns it on. And Kubernetes will deploy for Ceph, and it just works. You don't have to do anything else. So we're taking advantage of the container deployment to get as much scalability as we need in response to demand, and setting it up as simple as possible for the operator. Yeah, go ahead.
So on the second bullet point here is we're talking about adding support for before migration. So one of the problems we have now is, like Patrick said, the NFS clients are sort of bound to a particular IP address. And so what we want, but there are mechanisms in the NFS client, in the kernel, Linux kernel NFS client, that will allow it to move to a different one. And so we could leverage that to be able to do things like scale down a cluster. So if we've got, say, a 3 or 4 node cluster, and we want to scale down to one less, we could migrate everybody off of that node and onto other ones, and then they could go and then we could just decommission that node. And then we were also talking about optimizing the grace period for subvolumes. So we really don't need to put everybody into grace if they are not exporting the same things. So we want to be able to, we could sort of re-optimize this work so that we only confine the grace period to nodes that are exporting stuff that a rebooting node is also exporting. And then finally, we want to eventually would like to do some sort of SMB integration, probably using Samba. And we have some ideas about how to do that, but it's a bit of a bigger project. And with that, that's the talk. So any questions? Okay. No questions. Okay. Well, thank you for coming. So.